multiplicities. So in this sprint, we have added support for situations when we are connecting several class instances to the same port. For example, let's consider this port multiplicity 03 example. And now I will open, I want to open a state diagram for this. I don't see any state diagram here. Just a moment. So for this capsule top, yes, yeah, I want to open a structure diagram. So in this diagram, it demonstrates the situation. So here we have a port PB, and we have 4 capsule A instances or parts of capsule A, and all of them are connected to this port PB. For each part, we have port P, and it has multiplicity 1, which is the default one. But since we have 4 parts, then the multiplicity of this port should be 4. And when connecting at runtime, we should build the structure properly and adjust the indexes when we connect part A to this port PB. For example, this part 1, it should be connected. It is connected first, as it here it comes first in this definition, and it will be bound at index 0 into this PB port. Then next comes part 2, and it will be bound at index 1. And then we also have part 3 and part 4, and they are optional capsule parts. It means that we are creating them ourselves at runtime. So initially they are not incarnated, but then when the model is executed, they are incarnated and also connected to this port PB, and they will be connected to index 1, to index 2 and index 3. So index 0 and index 1 are for part 1 and part 2, and then these ones come at index 2 and index 3. So at runtime, when we build the structure, then we should adjust the indexes so they are connected correctly. And this is, if we check the generated code for this capsule top, I think I already have code, but just in case I can build it again. This is generated code for top. And if I check here at the end, we have a special function called follow_out_v that is creating the structure of the model, and it is connecting ports between each other, and different parts and ports it's connecting between each other. And we can see that for part 1, we are connecting port P to port PB, and part 1 will get the default index, which is 0. But then when we are connecting part 2, the index in part 2, this port P will always, it has only one instance and multiplicity 1, and it will have index 0 when we are connecting at runtime. But when we are connecting it to port PB, it should be put, the index should be adjusted, because the first index 0 is already occupied by part 1 and port P of this part. So the next one the next index should be adjusted. So here we see +1, then it is +2, and then it is +3. So these adjustments are now properly generated by the code generator. We can see what is happening at runtime here, and this test case, it is checking for RT-bound events. This is a special event that we get from the port when it is actually bound to some other port. And we can see that we get these events because we define this port with this special keyword notify. It means that each time the port is bound, we will get this special RT bound event. So if we run this example, we can see that it executes properly, and the connectors are executed also properly at runtime. The ports are bound. So first we are creating part 1 and part 2. We are creating the top capsule here, and then the first 2 parts are bound. And they are bound at index 0. So here we see at index 0 and index 1. Then we are creating parts, capsule parts at runtime, and they are also bound properly. So we can consider one more similar example that demonstrates how the ports are bound at runtime. This is the example Multiplicity 1, and this model is originally contributed by Queen's University. So we have slightly changed it, and now it also operates as a test case. It is similar to the previous example, but if we see here the structure diagram, we can see that now we have port P1 of capsule B, and it is connected to 3 instances of capsule A. We have A1, A2, and A3, and also we are connecting back, all of these 3 instances are connected back to port P2 in capsule B. And in this example, in this test case, first we are sending an event, and it is sent to port P1, and when we just send it, it will be broadcasted to all 3 instances. Then all these 3 instances are receiving an event M, and now it has a parameter 42. Then all each of the instance of capsule A will get this event and will send a reply with different values. So A1 will send a reply with 1, A2 will send a reply with 2, and A3 will send a reply with 3. So this structure also should be correctly bound. And if we see for this example how the generated code looks like, we can see that here we also are adjusting indexes properly, and when we connect A1 to P1, so when we connect an instance of capsule A to port P1, in instance A, the port has it has only 1 multiplicity, it's only 1 instance, but in B it's 3 instances, and the first is connected just as is, but the second is adjusted, the number is adjusted, and for the third one the number is also adjusted. And when we are connecting to the opposite direction, so when we come from B, connecting B to P1, then we are adjusting to the opposite direction, because in P1 in B it has multiplicity 3, but in capsule instances the multiplicity is 1, and the indexes are also corrected accordingly. So here we see that we are adjusting by subtracting some number, -1 and -2. So this example is also now working good. If we execute, we can see that we are sending, the event is properly received by all three instances, then they are sending a reply. So here we are receiving, here we are sending a reply, and capsule B is receiving a reply from all these three instances. So the connector structure is properly created at runtime, and all the indexes are bound at proper places.